Hello friends, in today's question, a particle of mass m is projected at time t equals 0 from a point P on the ground with a speed v0 at an angle of 45 degree to the horizontal. Find the magnitude and direction of the angular momentum of the particle about P at time t is equal to v0 by g. So we have a particle which is projected from a point P, and let us suppose this is our x direction and this is our y, and the particle is traveling like this, and let us suppose the position of the particle at time t is equal to v0 by g is somewhere here, and let us suppose that is given as q, and r is the position vector of this particle and whose coordinate is given as x comma y. So you can say at time t v0 by g, the position of the particle is given as r, and which will be equal to xi plus yj. So this is the position vector of the particle at time t is equal to v0 by g, and we have a velocity initial that is v0 and angle of projection is 45 degree. So we can divide this velocity into two components. One will be in x direction, that is v0 x, and another one will be in y direction, that will be v0 y. So we can say the velocity v0 will have two components. First one will be along x-axis, which we can say is a horizontal, and given as v0 x, which will be equal to v0 cos of 45. So this will be v0 divided by square root of 2, and next will be along y-axis, which we can call as a vertical. So we have v0 y is equal to v0 sine of 45, and which will be also equal to v0 square root of 2. Now after time t, which is equal to v0 by g, we can find out the vertical component. So we can say after time t is equal to v0 by g, the vertical velocity component let us represent that as capital V of y, and which will be equal to V of y minus g of t, where V of y is initial velocity, acceleration due to gravity is g minus g, and t is the time. So we substitute the value of v0 y, which is v0 square root of 2 minus g, and time is given as v naught by g. So g goes away with g, so we get vertical component of y, and you can say that is at point q. At point q. So v naught y will be equal to v naught we take common, so this will be 1 about square root of y minus 1, and we can say v naught 1 minus square root of 2 divided by square root. So this is the vertical component of the velocity at point q. Okay, or we can say after time t is equal to v naught by g. And but the horizontal component remains same during the entire projectile motion. The horizontal component remains same. Therefore, you can say capital Vox is equal to Vox, and that will be equal to v naught upon square root of 2, and this is the velocity at point q. At point q. Therefore, we can find out the velocity vector at point q. Therefore, velocity vector after time t is equal to v naught by g, that is at point q, and let us suppose at point q, so this is point q, and we are going to find out, we already found out the position vector, that is r, which is x, I and yj. Similarly, we can find out its velocity vector, and we can say, which will be given as v will be equal to Vox I plus Voy j. We substitute the value, we get v naught square root of 2i plus v naught, and here we have 1 minus square root of 2 divided by square root of 2 and j. So we got the velocity vector at point q, that is after time t equal to v naught by g. Now we can find out the distances traveled in vertical direction as well as horizontal direction in time t is equal to t naught. So we can say in time t is equal to v naught by g, the horizontal distance traveled by the particle. Distance traveled by the particle, and let us call that distance as x. So that x will be equal to horizontal velocity multiplied by time t. So we have, this is v naught by square root of 2, and time is given as v naught by g. So we get distance x is equal to v naught square divided by square root of 2 and multiplied by g. So the distance traveled in, you can say, x direction. So this is the horizontal distance, that is x, and this will be our vertical distance, that will be our y. So we can get the position vector xi plus yj. And next is our vertical distance traveled. By the particle, and is given as y, which will be equal to VOY plus minus rather, because acceleration due to gravity, g t square. VOY is V naught square root of 2, time is V naught by g minus half, and this will be g and V naught divided by g whole square. So we can say for y will be equal to, this will be V naught square divided by g square root of 2, and we have minus half, this will be g V naught square divided by g square, and g square cancel with g, so we can take V naught square by g as common, so we can say this will be equal to V naught square by g, and we have here 1 by root 2 minus 1 by 2. Therefore, the vertical distance y will be equal to V naught square by g, and this will be equal to, LCM will be equal to 2 root 2, and we have 2 minus root 2. So we found out the vertical distance y. So therefore, we can now write the position vector of the body, which is given as xi and yj. Therefore, position vector of the particle at time t is equal to V naught by g, that is at point Q. So we know that's given as R is equal to xi plus yj. X is our V naught square divided by g square root of 2 I, plus y is V naught square by g, and this have 2 minus square root of 2 divided by 2 root 2 multiplied by g. Now we can find out the angular momentum. Angular momentum about point P. You can say angular momentum about point P. Let us suppose that is represented as L. So we can say LP will be equal to M, and we have here R cross V. So R is a position vector and V is the our velocity vector, which we already found out. So this is our capital V. We substitute the value, we get M. R is given as V naught square divided by g square root of 2 I plus V naught square divided by g, and here we have 2 minus square root of 2 divided by square root of 2, and cross velocity vector is V naught square root of 2 I, and we have plus V naught divided by square root of 2, and we have 1 minus square root of 2, and bracket closes. Yeah. Now we can simply use the cross product, find out the solution. So we can write this as, this will be equal to m. We have I, j and k, and I will be our v naught square upon g square root of 2, and here I will be equal to v naught square root of 2, j will be equal to v naught square upon g, this is 2 minus square root of 2 divided by square root of 2, and here will be v naught upon square root of 2, 1 minus square root of 2, and we have 0 as well as 0. Now we open this, we get m, and it will be equal to v cube divided by g2, 2g, and 1 minus square root of 2, and this will be minus, and once again it will be v naught cube divided by g square root of 2, and this will be equal to 2 minus square root of 2 divided by square root of 2, and k unit vector. So this is cube, not square. Now it is a simple calculation. Now we can take this entire thing as common, so we can write this as m v naught cube divided by g, and we are left with 1 minus square root of 2 divided by 2, minus this will be equal to, I think there is some mistake, position vector r, yeah, 2 root 2, yes, 2 root 2, and this will be also 2 root 2. And this will be 2 root 2. And now it's okay. So here we get 2 minus square root of 2, this will be 4 into k unit vector. So we get this as m v naught cube divided by g, and taking 4 as LCM, we have 2 minus 2 root 2 minus 2 plus root 2, k unit vector, and plus 2 and minus 2 goes away, and we are left with this as minus m v naught cube divided by g, and this will be coming as root 2 by 4. So we can rationalize it, and this will be giving us k unit vector. So almost done now, simple calculation is left. So we can say our angular momentum LP at point P will be equal to, this will be minus m v naught cube upon g multiplied by 2 divided by 4 root 2, and with k unit vector, and we can cancel this 2, so we get angular momentum will be equal to minus m v naught cube divided by 2 root 2 multiplied by g, and we have a k unit vector. So this is the, you can say, moment of angular momentum with respect to point P. This is the angular momentum about point P, and its magnitude is given as mv0 cube divided by 2 root 2 g, and the direction will be in the negative z direction because x is minus, sorry, k unit vector is a negative, so we can say direction in negative z direction, and which will be perpendicular to the plane of motion and into the plane, So this completes the question. Thank you.